Section 6.2, integration by substitution. We've come to the point now where we've done our basic integration and we've worked with that power rule for quite a bit the entire time. Well, what happens when we can't integrate very nicely, or the things aren't set up very nicely to be able to integrate? That's where our integration by substitution comes in. And there's a few things that we're going to look at in order to be able to tell what kind of values we're going to be substituting. So we use integration by substitution for that more complicated, more complex derivative. We normally call this integration of composite functions. If you remember, a composite function is a function within another function. So let me go ahead and turn this paper over. If we give you a g of x equals, say, x to the third, and h of x equals the quantity of x minus 3. If I ask you to find g of h of x, that tells us to take h of x and plug it in for our x's in g. So we'll have x minus 3 to the third. Well, in order to be able to integrate this at this point in time, we'd have to multiply x minus 3 out 3 times, or use Pascal's triangle. What integration by substitution is going to allow us to do is integrate it without having to multiply that out, which nobody is going to want to do. So we call this u substitution. We're going to let u equal some function. Normally it's the inside part of a composite function. We're going to find du by taking the derivative of that u substitution that we did. We're going to complete a full substitution, which I'll show you in a second. We're going to find the integration, substitute our x's back in, and then we really don't want to forget that c, unless it's an initial value problem, which we'll be able to find the c later on. So in example 1, notice we have the x minus 3 to the 5th, very similar to that problem that I just showed you that was a composite function. So if I ask you to multiply, or to find the integration of this, we would have to multiply that out. We would take x minus 3, multiply it out 5 times to get just our integrin to be able to integrate it. But here, suppose we let u equal x minus 3. And u, again, is a variable. It's very arbitrary. As you get to doing some of these problems, you're going to notice, hey, that's going to be my u. And at this point, our u is normally going to be the stuff in that quantity. So if I let this u equal x minus 3, I would have the integration of u to the 5th dx by just substituting that u equals u for x minus 3. The problem here is that we have now u's in our integrin, and our variable of integration, remember, is x. Remember, from the very first days of integration, this variable of integration has to be the same as the variables in the integrand. So I need a relationship between u, or du, and dx. And the way I'm going to get that is coming back over here to my substitution, my u, and finding the derivative of this. The derivative of u with respect to x is du dx. The derivative of x is 1. If I take this dx and multiply it over, I end up with du equals 1 dx, or just dx. Now, because we have a relationship between u and x and du and dx, I can take this information and substitute it back in to my integrin. So now I'm integrating u to the 5th du. It's not always going to be the case that our du's and dx's and our variables all kind of nicely cancel out. In the first several problems they're going to, will get a little more complicated as the days go on. Now I can integrate u to the 5th du. Integration of u to the 5th is u to the 6th over 6 plus c. But remember, we're not interested in what u is, we're interested in what f of x is. So f of x, we're going to replace that u again with x minus 3. So I have x minus 3 to the 6th over 6 plus c. And there is my original function, f of x. Example 2, we're again going to see that we have the integration of 4 times 4x minus 3 to the second dx. We could, and I would expect some of you to, go ahead and square that out, find the integration, and be done. What I'm going to do today is to show you what the u substitution is going to look like. So I'm going to let u equal 4x minus 3. Again, we're going to notice that 4x minus 3 is the inside of that quantity. So if I come back to my integration, I end up with 4 u squared dx. Again, our variable of integration and our variable within the integrand are different. So to get them to be the same, I come back to my u. I'm going to find the derivative of it. So again, du dx is going to equal 4. Derivative of 4x minus 3 gives us our 4. Taking our dx over, we know that du is going to equal 4 dx's. Well, if I look at my integrand, I have 4 dx's here. Because remember, this is 4 times u squared dx. So 4 dx's equals 1 du. So again, I'm going to integrate. I have u squared du. And one more time, I have a nice clean integration and substitution. Integrating u squared, I end up with u to the third over 3 plus c. So my original function, f of x, is going to equal the quantity of 4x minus 3, that's what our u was, to the third over 3 plus c. Example 3, we're going to see something just a little more complicated. 1, we have a numerator and denominator. Well, what do we let our u be? Because we don't have actually a quantity. But if you think about the denominator as being in parentheses, we can bring this entire denominator to the numerator by making it a negative exponent. So now I have that quantity to an exponent. And if you don't like that, we're going to see where if we have a fraction, the denominator is normally going to be our u. Not always, but generally. So now I let u equal, I'm going to let it equal that x to the fourth plus 2. Coming back to my substitution, I end up with x to the third times u to the negative first dx. Coming back to my u, I'm going to find the derivative. So I know that du is going to equal 4x to the third dx. I've already moved my dx over. Most of you hopefully are going to see that. It's always going to move over. Well, if I notice now 1 du is going to equal 4x to the third dx's. If I come back to my integrand, I have an x to the third and I have a dx. I don't have that 4. So what I need to do is to move that 4 over to the du. And to do that, I'm going to divide both sides by 4. So 1/4 du is going to equal x to the third dx. Now, I can replace that x to the third dx, which I had, with 1/4 du. So my integration becomes 1/4 u to the negative first du. Again, same way these are split up here, I can split these two here as well, because it's x to the third times u to the negative first, and this is 1/4 times du. Now I can go ahead and integrate my 1/4 u to the negative first. Remember that u to the negative first, that really meant 1 over u. So I can think of this as 1/4 the integration of 1 over u du. And when we have 1 over u, the integration of that is the natural log of the absolute value of u. Replacing my u with x to the fourth plus 2, I have 1/4 the natural log of the absolute value of x to the fourth plus 2 plus c. Now, some of us in our answers are going to see that these absolute values really aren't necessary. We're going to see them as a quantity. Why is that? Well, if I take x to the fourth, I'm always going to get a positive number. Plus 2 is always going to be another positive number. So I could really write this as 1/4 the natural log of x to the fourth plus 2 in parentheses plus c. Not a big deal to me if you leave it as the absolute value or in parentheses. The only problem would be is if it had to be an absolute value. So if you leave an absolute value, you're going to leave yourself with little error as an answer. I have just a couple more examples. If 3 equals x minus 5, 3 over x minus 5, the integration. So here, we're going to let u equal an x minus 5. So du equals dx. As I integrate, I'm looking at 3 then over u du. I know it's kind of quick, but remember u was x minus 5. I have to find the derivative in order to get the same variables. So du dx equaled 1. Multiply the dx over, du equals dx. Here the 3 stays, can't get rid of it, but our x minus 5 became u and dx became du. That 3 really isn't a big deal. So I can write it as 3 times the integration of 1 over u du. Here we have 3 natural logs of the absolute value of u plus c. Replacing our u, we have the natural log of the absolute value of x minus 5 plus c. Now here would be a case where we couldn't take these absolute value symbols away and make them parentheses, because if x was say 2, we'd have 2 minus 5 gave us negative 3, which we could not take the natural log of that value. So we have to leave the absolute values there. Example 5, last one for the day. We're going to let u equal, again, that quantity, 2x to the third plus 5. du is going to equal 6x squared dx. So notice over here, here's our u. So we have the integration of 4x squared times u to the third dx. Well, if I think about 6x squared, I have the x squared and I have the dx, and those are pretty easily seen. What about this 4 and what about this 6? Well, I can think about this 4 as being 2 times 2 if I want. I can think of the 6 as being 2 times 3, so they both have a 2 in common. What I like to do is, since they don't match exactly, just go ahead and divide the 6 over. So we have 1/6 du equal x squared dx. Bring that 1/6 in with the 4, so we have 4 over 6 u to the third du. And now we can work on, well, what actually happens? Well, our 4 divided by 6 is actually 2/3. So we have 2/3 the integration of u to the third du. Integration of u to the third, we have u to the fourth over 4 plus c. 2/3 times u to the fourth over 4, our 2 and our 4 will cancel. So we end up with u to the fourth over 6 plus c. Or if you want to think of it as 2 over 12, gives us 1 over 6 as well. Replace your u with 2x to the third plus 5. So that gives us our original function, f of x is going to equal 2x to the third plus 5 to the fourth over 6 plus c. And that gives us our first taste of integrating using the u substitution process.